Today on Inevitable, our guest is Arvin Gannison, CEO at Fourth Power. Fourth Power is building a flexible duration thermal energy system to meet the needs of an electrical grid that's increasingly powered by renewables. Their system heats liquid tin to extremely high temperatures, circulates it around carbon blocks where the heat is stored, and then converts that heat back to electricity on demand via thermal photovoltaics. They hope to be able to solve both short-duration energy storage use cases of 5 to 10 hours and long-duration needs of 100 hours or more, with the ability to discharge power within seconds. Fourth Power raised a Series A at the end of last year, led by DCVC, with participation from Breakthrough Energy Ventures. Arvin has a fascinating bio, which includes time in the U.S. Senate as senior policy advisor to the late U.S. Senator from New Jersey, Frank Lautenberg, over 5 years in the U.S. Environmental Protection Agency, and nearly 6 years at Apple as the head of global energy and environmental policy. We discuss the path he took through his career, his decision to join Fourth Power, and all about how the company works and why it matters. From MCJ, I'm Cody Sims, and this is Inevitable. Climate change is inevitable. It's already here. But so are the solutions shaping our future. Join us every week to learn from experts and entrepreneurs about the transition of energy and industry. Arvin, welcome to the show.
Cody, thanks.
Well, boy, we're going to talk about an incredibly important topic right now, which is that of energy storage. But before we dive into all the work you're doing at Fourth Power, I'd love to have you explain the different paths your career has taken, because you've worked in some incredibly interesting roles along the way that I'm sure are informing the work you're doing today.
Thanks for the question. I wish I could say this was what I planned, but essentially every risk I've taken has just opened a lot of different doors. So yeah, I started off, this is now 25 years ago, as a bond trader. And that is about as far away from what I do now as you could possibly get. And then 9/11 happened. And that was a moment for that industry where I think a lot of people were thinking about meaning and value and contributions. So my career pivoted immediately then. I then went to a sustainable or a socially responsible investment firm, then became an advisor to a senator. And then next thing you know, I was appointed by President Obama to be a regulator at the U.S. Environmental Protection Agency. And that was like such an interesting point in time, right? That was 2009. I know that is probably a lifetime away, feels like a lifetime ago. But at that point, coal was still largely dominating the electricity grid. And we talked about natural gas as a bridge fuel. The economics of solar and wind were not there. They were still not cost competitive. But that was really an inflection point as regulations and economics started to change the way that the grid worked. After that job, I went on to lead global energy policy for Apple. And Apple is not only a large consumer of energy, but its supply chain is even a larger consumer of renewables, of electricity. And the company, really under the leadership of Tim Cook and Lisa Jackson, wanted all of that to be consumed, that electricity to be renewable. So that is fairly straightforward in the United States. You can sign a PPA, you can do a green rider through a utility program, lots of different ways. But Apple's supply chain is largely overseas. So it meant working directly with regulators, with utilities, and with state grids in countries all around the world on how to adopt the views and requirements of consumers into how a grid works. And this is a pretty foreign concept to a lot of grids. So I did that for close to 6 years. And about a year and a half ago, I took the leap to become the CEO of Fourth Power.
Boy, there's so many angles we could go with that. We're going to dive into at some point. I have to get your thoughts on permitting reform and how transmission lines are going to get solved, at least in the US. But maybe explain how you went from a regulator at the EPA to a leader and executive at Apple to deciding to dive into a startup in the heavy infrastructure, clean energy space. What did that leap look like for you?
Yeah. So again, there's no path. I really think we look back at our careers and we kind of draw connections when they don't necessarily exist. This is not what I was planning for. When I left Apple, I went to a place called Advanced Energy United, which is a clean energy trade association. I did that for 2 years before I went to Apple. And I actually learned that even though I knew the electricity system from a regulatory perspective, I didn't really understand how energy markets worked. I didn't understand how wholesale markets work, didn't understand the business model that utilities have in vertically integrated states. And that time in Advanced Energy United was like a boot camp in really understanding the wonkery of how the machine works. And I pivoted off of that to lead this program at Apple. And that was a leap that made perfect sense to me because Apple's perch as a consumer is extremely large. Their leadership is extremely motivated on these issues. And at that point, I'd never worked for a for-profit entity before. So all of these things are leaps and they're a bit of risks, but it felt like a good one to take. And last year, when I decided to leave Apple to become the CEO of Fourth Power, which at that point hadn't closed any funding, right? It hadn't closed its Series A funding. It was largely because I'd seen the modeling. I understand the shift that the electricity system is taking and how the backbone of that will be storage in 9 out of 10 scenarios. And it's policy agnostic in many ways. And I also knew that in order to crack this issue of decarbonization, we need storage at a scale that existing technology just does not support, right? The cost of storage is very high. And so I knew that there needed to be technologies that represented like a economic step change down in terms of cost. And then personally, I was pretty reluctant to take a CEO job because I have 2 small kids. And it wasn't until I met now the CTO, the founder of this company, Dr. Ashegun Henry, where I realized this was somebody that was worth taking a risk with. And here we are. I had a couple of other offers from clean tech companies, and I reached out to a friend or a person I knew at Breakthrough Energy Ventures, who's now an investor of ours. And they said, hey, before you accept any of these jobs, why don't you talk to this guy? And I was like, okay, I don't know him. But again, we have 2 small kids. And so I met him and he's like, okay, let's meet at a cheesecake factory. I was like, cheesecake factory? I haven't been to a cheesecake factory since I was like 11 years old and I had the metabolism of an 11-year-old.
You need a 1,500 calorie salad.
Yeah, exactly. And I guess you kind of have to have the cheesecake when you're there. So like, there you go. And he showed up with his kids, right? He showed up with
That's
3
awesome.
of his kids and he didn't know how important this was to me. And I still, phones go down at 6 from 6 to 8, barring absolute catastrophe. He didn't know how important that was to me. But then when we were able to sit down, I realized that there was a world where I could be a CEO of a company and also really you only get 3 hours a day with your kids. Have those 3 hours untouched.
And what about the company itself pulled you in?
It was supply chain and cost, right? Well, I think we'll get into this in a little bit, but we've done some modeling that if you want to support a renewable grid or decarbonized grid, you need a lot of storage. The amount of storage that has to date been deployed is 0.1% of that total. So we are making a lot of progress. There's a lot of storage coming on the market, but to get to the amount of storage you need, it needs to be super cheap. And that's what this technology is. And it needs to scale, right? We can't rely on lithium mining, both as it relates to electrifying everything and also doing grid level storage. So the storage medium and how the application works needs to be kind of coming from a perspective of abundance. And those are really the 2 main characteristics I thought would determine whether a battery company could scale. And this company meets those.
Mm-hmm. When I think of storage today, like I may be totally wrong here, but it seems like the type of storage that's most widely deployed is physics stuff, like pumped hydro, like water going up a hillside and running back down. Is that correct? And is it just, we just don't have enough physical sort of features near renewable power sources to enable that to be the long-term solution?
Yeah, right. Pumped hydro is geographically fairly constrained. You need to be around the geography to be able to do that. Lithium-ion is the other prevalent way to store electricity, but it's expensive and it can really only work for short durations of time. So what I'm saying is not against those technologies. I think that they're great, but I don't think they represent the uniform global scaling up of storage that we need to have.
And you all are trying to harness heat to be the storage mechanism, I suppose. I've had a few other kind of heat-focused companies on the pod, and most of them are trying to solve heat as an industrial heat source. And it's like, oh, and we can also do this storage thing. But it feels like you're coming at it from the perspective of, no, actually, it's a very efficient storage medium first and foremost. Was there a time when the technology was thought of as it could be an alternative to gas-powered steam, as an example, for industrial heat?
Yeah, so I think before I came on, Ashe, Dr. Henry, Ashegun, whatever you want to call him, right, this could be used for both purposes, right? It's storing huge amounts of heat at very high temperatures. But I made a decision fairly early on that the focus really needs to be on electricity. And that is no shade against folks who are focusing on industrial decarbonization. But here's the thought process. I'll start this with a fact that hopefully you and your listeners may have heard. A ChatGPT query will take 10 times the amount of energy as a Google search. So that's like a representation of the order of magnitude of electricity demand that we are going to face in our generation, right? Electricity demand has largely been flat during my adult life. It's about to change. And so when you look at the market for new electrons and high capacity electrons, it's large, it's growing, and it's global. If you look at the market for industrial heat, it becomes largely driven by customers who care about climate, who want to use decarbonized ways to provide power that natural gas would normally fuel now. And to those entities, hats off to you. I think that that's the thing that every business should do. But that's not a business model, or that's not a business model that scales into the trillions. Whereas electricity is life, energy is life. And if we are able to provide stored electricity at the cost that we're seeing, our competitors aren't storage companies. Our competitors become every form of electricity generation.
Can you explain what the product itself looks like?
Yeah. So to put this in your mind's eye, right, this is a large battery. At full size, it's a 100 megawatt battery. So that could provide enough power for hundreds of thousands of homes for a couple of days. Its duration, you can store energy for anywhere from 10 to 100 hours, and the customer gets to choose. The way it works is picture something about a football field in a warehouse. So it's not much different than any other power plant that you see from the highway. It takes electricity either from the grid or from on-site solar, and it can be in increments of 5 minutes, 2 minutes, 3 minutes. It doesn't quite matter. And it powers an industrial heater. That industrial heater, it's a resistive heater, heats up liquid tin to 2,400 degrees Celsius. And that liquid tin is pumped through two different systems. One is a storage system, a storage block system. These are blocks made entirely of graphite. A 100 megawatt battery has 8,000 one-ton graphite blocks, where the tin is transferring the heat and radiating that heat into these graphite blocks. Those graphite blocks store the heat for as long as you want, weeks, months. And when you want to convert it back to electricity, that heat is moved again from the graphite blocks to what we call a TPV power block. So the heat, of course, when it's at that temperature, is radiating just extremely power-rich white light. And that white light is converted back to electricity using thermophotovoltaic cells. Those photovoltaic cells are largely now used in applications like for spacefaring satellites, where you're converting solar into the satellite or space system itself. And the round-trip efficiency, of course, takes a bit of a hit. So this is the trade-off in our system. The cost of it is a tenth that of lithium-ion, and the round-trip efficiency is about half that of lithium-ion. But that doesn't really matter when you have large variations in the electricity grid and you're able to do arbitrage with more variation, which you'll see with a higher renewable penetration.
So if I understand it at a very high level, you're taking heat from the sun, converting it into electricity through, this isn't you, but through solar power or whatever. This is happening outside of your system. The electrons are showing up on your end. You're then turning them back to heat. So creating something very hot and then flowing that heat through a storage mechanism, and then eventually turning that heat back to electricity and sending it back out to the grid. That's the kind of the high level system, yeah?
That's exactly right. And the pipes, the pumps, and the storage material are all made out of graphite. And this is a really important point because graphite is a derivative of carbon. Carbon is the 10th most abundant element in the world. So by mass, over 99% of the system is graphite. So from a supply chain perspective, you're really not limited in the scale up.
If I remember correctly, graphite is often used on the anode side of a battery, I think. Is there a heavy China supply chain dependency on graphite today as well?
There is. There's also a domestic supply that is starting to grow because of the Inflation Reduction Act and a tax credit called the 45X tax credit that is starting to build development here. But the thing about graphite is it can be developed from any form of carbon. So you could take coal ash, you could take unutilized coal, and you could transform that into graphite. So the demand will really kind of drive domestic production as well as some of the tax benefits associated with using domestically sited graphite is really going to push production to the United States.
Got it. So you would argue that unlike, say, some of the other metals in a lithium-ion battery, which there's quite literally just a shortage on the planet Earth of these things, graphite as it exists as a raw material may not be super abundant today or may have a dependency on China, but our ability to essentially create it is less limited.
Yeah, and to be clear with graphite, like there are producers in the United States right now. So a way that a lot of graphite is produced in the United States, and also the quality of the graphite doesn't matter to us because the temperatures we're at, any impurities just get burned off. But a lot of graphite in the United States is produced from the end waste product of petroleum refining. And that is shipped and converted into graphite in places like West Virginia and Pennsylvania.
Okay, so you have these graphite blocks that are essentially storing this heat at incredibly high temperatures. You have this liquid tin that's circulating around them and transferring the heat from these blocks over to these, you call them thermal photovoltaics, which are, I assume, like solar panels, except they're accepting of heat as opposed to rays from the sun. Like, explain what a thermal photovoltaic is.
So this is an outgrowth of concentrated solar. So these are cells that we are growing with a specific recipe to only utilize the most productive part of the wavelength of light. And the rest is reflected back into the system. That's how we get to these high round trip efficiencies. So previously, these types of cells, I think the maximum we were getting for 20 years from the 80s was like around 20% or so. And we ended up getting 41% and got a Guinness World Record and a Nature paper published off of that. Recently, we've had some innovation there with the University of Michigan setting a new record at 43%. So we have ways to get up to 50% now.
Do you know roughly where like solar photovoltaics are today in terms of efficiency?
I don't know the number off the top of my head.
Yeah, I don't either. Okay. Yeah, I'm just curious how relative this is to that. But it sounds like you have, this setup where you've got mirrors sort of bouncing the heat or the light around. Can you explain a little bit more about what that looks like? Just, it's always helpful for me to get a visual of this stuff.
Okay, so think about this. So you have a huge amount of heat and a huge amount of light. So you need cells that are durable, that are able to have that exposure to heat and convert it in an efficient way. And you need it to be instantaneous in terms of response. So think about a rectangle that can dip in and out of the heat. And that rectangle is lined with these wire-bonded thermophotovoltaic cells. These are more like LEDs than they are anything else. It's from the same technology as LED manufacturing. When you want to convert it to light, these large rectangular rods dip in to convert precise amounts of light into electricity. And the system is designed to give you complete control on how much of this TPV you expose to light at any given moment so that you're able to maximize your economics and provide exactly the output that you want to provide to the grid.
But it's light at a certain temperature as well that matters?
No. So I'm sorry, I'm not being clear. The relationship between temperature and light is that the hotter it gets, the more light is emitted. And this is why it's so important to get to these high temperature regimes. You're getting to a much, much more energy dense amount of light than you would be if you were 500, 600, 700 degrees C lower. So we're largely at the physical limitations of graphite and tin. And we're getting temperatures that are among the hottest in the world in terms of the system. And that's how we're able to convert so efficiently the light into electricity.
I was tripped up on the name thermal photovoltaics. It's not actually the thermal property that's causing the transfer. It's that the thermal property drives a special kind of light.
Exactly.
Okay. Yeah, that makes sense.
It's really important. That's why we're called fourth power. There's a relationship between heat and light, where the hotter you get, you're getting that amount of light to the fourth power. So you're getting exponential amounts of light the hotter your temperature range is.
And then you mentioned currently, I think you said up to 43% round trip efficiency. You're trying to get to roughly 50%. Well, how does that compare? You said lithium ion has significantly greater efficiency, but it's just more expensive as a system.
Yeah, so this is kind of the interesting trade-off, right? So lithium ion has around 85 to 90% round trip efficiency, but costs 10 times as much to deploy. The issue is like round trip efficiency matters a lot when the price of electricity is stable or not all that variable. If you have a traditional dip due to solar, you can charge and discharge predictably over 4 hours or whatever. Our view is that the grid is actually going to start looking very different when it comes to the locational marginal price or the overall cost of electricity at any grid you're at. As you have more renewables, which by their very definition are variable by the minute, you're going to see more and more spikes and more variations in the cost of electricity. So that means round trip efficiency matters less, and what matters more is the ability to suck in that energy very quickly. And our system, there's one other piece that's really important here. It can charge the battery 2 times faster than it discharges. So we can suck in large amounts of energy when there's a dip in prices. And this is going to become really important as the world transitions to one with more variable generation on the grid.
Hey everyone, I'm Yin, a partner at MCJ, here to take a quick minute to tell you about the MCJ Collective membership. Globally, startups are rewriting industries to be cleaner, more profitable, and more secure. And at MCJ, we recognize that a rapidly changing business landscape requires a workforce that can adapt. MCJ Collective is a vetted member network for tech and industry leaders who are building, working for, or advising on solutions that can address the transition of energy and industry. MCJ Collective connects members with one another, with MCJ's portfolio, and our broader network. We do this through a powerful member hub, timely introductions, curated events, and a unique talent matchmaking system and opportunities to learn from peers and podcast guests. We started in 2019 and have grown to thousands of members globally. If you want to learn more, head over to mcj.vc and click the membership tab at the top. Thanks, and enjoy the rest of the show.
When it comes to variability, obviously we know solar is variable in a 24-hour daily cycle, but also in a seasonal cycle. Wind is basically unpredictable from a variability perspective, right? Like it will change dramatically. And I think compared to a grid 15, 20 years ago, which was either coal or gas, which was pretty darn consistent all the time, the grid that we will have in the future, depending on, in particular, how much wind I think comes online, will be incredibly hard to model, I would think.
Absolutely. And there's another interesting point, which is the more you have a grid that has these variable assets, whether it's solar or wind, the longer you need to store that energy. And that's because if you're starting to develop a grid that has 30, 40% variable resources, and you have a more cloudy week than expected, or storms or whatever, you need to be able to store that energy longer to be able to weather these events, which is why we've designed this battery to be anywhere between 10 and 100 hours of storage. And our utility customers can upgrade the amount of storage anytime along the way. So they're not building for a future scenario or undersizing it now, but they can kind of build what they need now and grow with the needs of the grid.
Are there any chemical storage solutions that are long duration like that? I mean, I think of batteries as being more kind of intraday type of storage, right?
I don't want to say no dispositively and get yelled at.
You will get feedback for sure.
Okay, so with that caveat, no. Things like lithium ion have about 4 hours of duration. If you want to get to 8 hours of duration, you're going to have to build a second lithium ion battery. I say that very generally. And so to get to these long durations, I think you're largely looking at different types of batteries. And our approach is that every grid is different. So you need to really meet your customer where they are and be very scalable and flexible for what the need is, because a grid in Texas is going to look super different than a grid in Pennsylvania. And we want to sell to both.
How co-located do you need to be to power?
You don't. You can co-locate with renewables, and you can essentially make renewables a baseload resource, but you can also be a distribution, it's a transmission level resource for utilities. And we're talking about both. I think that utilities who want standalone storage are in deep need of technologies like this.
So I guess behind the meter or in front of the meter sort of solution, if you want to use the language.
Yeah, although I shouldn't have said distribution because this is not a behind the meter resource. It's way too big to be behind the meter, and the value is largely for utilities to utilize it. However, if you're an IPP, if you're in a deregulated market, the business model would allow independent power producers to use this to essentially hedge on renewable costs.
But this is a utility grade solution. You wouldn't see a private company raising capital to put this near something where they have a significant amount of storage need.
You mean like a hyperscaler?
Yep.
Yeah. I mean, look, I think that there are some hyperscalers that are starting to think about what it means to island, what it means to be kind of off grid. But the vast majority of hyperscalers are working with their local utilities on how do they invest in technology to avoid rate shifting, avoid costs on the utility. And that's where there's a interesting partnership between companies like us, utilities, and hyperscalers.
To some extent, there's fixed cost. Given the system you described, it seems like you have to be of a certain size for it to matter. You talked about 100 megawatt hour type of solution.
100 megawatts, yeah.
100 megawatts, excuse me. Is that the storage capacity you're looking for?
Yeah, I think this will be about a 1 gigawatt hour battery. So let's just call it 100 megawatts, 10 hours of storage. It could be 5 times that. And so, yeah, I mean, most data centers will need, that's pretty large for a data center, but not all. I mean, there are some data centers that are approaching that amount of electricity need. And it's really how do you solve problems for the utilities as well as the hyperscalers. I think that if you're a hyperscaler and you're building data centers, you're having some like license to operate issues where their demand is either causing a burden or causing, at the very least, a lot of stress for utilities on how they meet the demand of these hyperscalers without shifting costs or without over procuring that has the implications of shifting cost onto other ratepayers. And that's where technologies like ours kind of fits in.
At the top of the show, I said, hey, let's talk about permitting reform and sort of what needs to happen with transmission lines. It sounds like you're not necessarily super dependent on that needing to get built out, though.
No, we're not. I mean, I think that we're largely dictated by economic. I mean, I have a lot of thoughts on permitting reform because put aside the next 5-10 years of our growth, it's going to be really important to just build. But there's a lot of old natural gas. There's a lot of interconnections that are coming offline, and they need stable grid resources that have similar capacity factors as what is being retired. So there is plenty of interconnection for an asset like ours in the short term. In the long term, we need much more when it comes to interconnection and transmission.
How do you help utilities look at a solution like yours and make trade-off decisions relative to other things they may be considering that may not even be storage? It may be upgrading other parts of their infrastructure, but to some extent, they only have so many dollars they're able to spend in not just 1 year, but in like a 5-year period.
Well, and this is a really interesting implication of climate change, right? I think utilities are spending more and more money on fire mitigation, on vegetation management, and that's taking away from utilities' ability to invest in new technologies. But I think what's fundamentally happening is we're not looking to reopen or change the utility business model, right? If you're a vertically integrated utility, their business model is fairly simple. I mean, it's not, and I'm saying this generally, but utilities they have a certain amount of money they can spend, and they can earn a guaranteed rate of return on the capital that they spend. But the operating expenses go to that full amount that they can spend. And so resources that are more capital intensive, but have less operating costs or OPEX are super favorable. Natural gas, for example, it's roughly 60-40. meaning 60% of it is capital, 40% is ongoing operational expenses. Technologies like ours are closer to 90% capital and 10% operating expense. So it's very clear why that works within a utility business model. And so utilities are in such demand and such need to find ways to get new electrons on the grid. It's really important for technologies to understand where their customers are and not try to change their customers to meet your technology, but make sure that your technology fits in with how your customers do business.
I'm starting to hear some anecdotal stories from portfolio companies of MCJ or other startups I talk about that are saying utilities right now are, in many cases, trying to push storage even into small instantiations on the edge of their customer base rather than have to invest in refactoring their transmission lines, right? So this is not building it on their end of the meter to store utility grade power. It's actually helping their customers manage intraday power load themselves to create efficiency for the utility.
And I think this is like such an important and great point you just made. I think that the stresses on the utility today in 2024 are fundamentally different from what they were in 2014 or 2004. And we are at a moment where the ability to reliably store and move electrons comes at a premium. So I think that utilities are extremely good customers for technologies like this.
And where are you all in terms of progress? Where are you from a technology perspective? Where do you hope to be in the next couple of years?
Yeah, so just for context, this technology has been built in the labs of MIT and Georgia Tech for the last decade. This all started with DOE funding in 2012. And a lot of the initial de-risking, so building a pump that can move tin at this temperature, building storage blocks, building a graphite system that doesn't corrode, the heater, so to avoid arcing, all that stuff was built in the lab over the last 10 years. Our challenge is how to scale it. And so where we are now is we're building our first demonstration. This is at a facility about 30 miles north of Boston. It's small, right? It's a 1 megawatt hour battery. It's tiny compared to our large footprint, but we're using full-size parts for it. So we're using full-size pump. We're using full-size graphite pipes. Everything is the same size as a 100 megawatt battery. So by sometime next year, we'll have our first demo completed. We've had some really great news recently with the pump and some other areas where we've retired a fair bit of risk. And we will be announcing at some point in the next several months our first pilot facility and where that'll live. That'll be a megawatt battery for stored for about 10 hours. And that's going to be exciting news.
And you all closed a Series A at the end of last year, I think. Is that right?
Yep. It was led by DCVC. It was about a $20 million round, led by DCVC and Breakthrough Energy Ventures, both of whom have representatives on our board. And we are using that money to scale, to build, and to accomplish this demo.
And for you, how's it been transitioning into a CEO role?
It's been great. I really like learning a lot of things that I don't know anything about. So I understand energy markets. I love learning about things I would otherwise never have learned about. So like things like intellectual property, all these things. How do you find a lease? All these things that I've never worked on before. These jobs are just fascinating if you are intellectually curious and you're able to make decisions based on incomplete information. And those are like the two things that I thrive on.
And it feels like today, a lot of what the company is probably needing to do is get this end-to-end system going, do a lot of tech de-risking and whatnot, but also be able to prove to your current investors and a future set of investors that, hey, no, there's commercial market interest in this. Here are the conversations we've had with utilities. Here are conversations we've had with hyperscalers. Here are some LOIs or whatnot that we can show, showing that there's commercial traction. You've talked to regulators. You've talked to whatever permitting work that would need to happen to build a facility somewhere. You might have a first idea of where you might go to market, like all that, right?
And all of that, we have an awesome team. I have really great people working with me, but also the technology speaks for itself, right? The market need is so clear. I think that when you talk to investors, regulators, utilities, it's really about understanding what it is they need and describing your technology in a way that resonates with them, right? Utilities And grid operators and generators, people spend like 10 minutes a year thinking about electricity, and they're not thinking about where their electrons are coming from for the most part. They're thinking about, is my power on and am I paying too much for it? So utilities are very conservative. They just need the lights on and they need it to be cheap. So I think we've done a great job of really listening and being with our customers to work within the environment that they've worked in for centuries.
So when I think of what the future would be with Fourth Power, it's sort of thinking of a world where you're taking a lot of electricity that is maybe generated when you have an excess of it. You know, it would otherwise today be curtailed. You're turning it into heat. Once something is at temperature, it's fairly inexpensive to keep it at temperature. So you're able to continue to store it, recycle it, reuse it. And then you've built this system that then can convert it back to electricity essentially on demand and send it back out. The vision is that there are these systems integrated in with our utilities all around, I guess, the country and the world.
Exactly. One point, which is like, I think a lot of people in the space talk about using electricity when it's free or when it's cheap, and that's ideal, right? Free is better than paying for something. But this is why the cost of the battery matters so much. I mean, when you have a low cost system like this, it's not necessarily about when the price of power dips below zero, but it's just when is there a dip? When is it cheaper to buy power? And there's economics around that. But since the system cost is so comparatively cheap, don't rely on curtailment or negative prices.
Given that, I'm curious though, it seems like if you're building a system that thrives on buying power when it's cheap and then selling it when it's expensive, why would this only be a utility-based technology? It seems like a lot of companies could run this thing and make a lot of money running it as a power broker.
For sure. And that is a business model that allows, right? I think if you're an IPP, if you're like a company like NextEra, a company who is an independent power producer, there's a lot of money there for you. Obviously, hedging a little bit on whether this company will become a power broker and become a trader, or whether we're going to support companies that want to be. I think that those are business decisions that we're kind of toying with right now.
Yeah, totally fascinating potential ahead of you. And I can't wait to see how it evolves. Anything we should have covered that we didn't talk about?
Actually, there's one thing I want to say about just kind of optimism in the market. I've worked in the climate space for my entire career, and I think in the next 3 or 4 years, there's been so many shots on goal that have been taken, and so many companies like Fourth Power, not even necessarily just in the electricity storage space, that are where we are, which is like de-risking close to market, where it's just going to be so great to see companies in all sorts of climate sectors start to sprout, because that's really what the last 4-5 years have been about. It's been the incubation of these technologies. So I'm really excited.
I'm excited for sure. I also wonder what that bake-off process looks like as things need to go from, hey, we're going to do some pilots here or there, to we're ready to deploy 10 of these across the country. There are definitely going to be winners and losers in that regard. I mean, as much as we all say, hey, let's let 1,000 solutions bloom, the reality of it is people ultimately want to back something that is going to be adopted in lots of places in lots of ways.
Yeah, I mean, to use the 1,000 flowers blooming or 1,000 trees growing, maybe they all take root, maybe they all germinate, but eventually some trees are going to shade out the others. And that's going to happen here. But it's really important to have all these seeds grow, because there's also a lot of ideation and competitive motivations that are causing this to bring out the best in each other. So I take a slightly longer view, though. Right? The market dynamic is, how do you get the capital allocated to the amount of scale up that we need to do?
Mm-hmm. I mean, it feels like that's the chicken and the egg. I feel like many capital providers want to see what is going to win before going all in, and yet you need the capital to get to a certain amount of scale to have the opportunity to win.
I do think that the Department of Energy, to their credit, has identified this, right? When ARPA-E came up in 2009, right? I think that they were trying to solve a problem. They solved some of the problem, but there's still this capital need that you're describing right now. I think what DOE is doing that right now with the Office of Clean Energy Demonstrations, kind of laddering into the Loan Program Office, is trying to address this very clearly. And you can see, at least in the DOE space, some of that starting to bear fruit.
In that technologies are getting government funding where there's clear commercial interest and where they can come up with a very clear sort of initial deployment, but already have a roadmap for what the next N of those might look like. Yeah.
Exactly. And this, again, gets to supply chain and it gets to scale. I think that the other lesson of the last several years is you really need to understand your supply chain and understand that your supply chain can support the amount of scaling that you want to do.
That's a great plug for an interview I did a few months ago with Julia Sicardo, who runs the DOE's Office of Manufacturing and Energy Supply Chains. It's a great listen for anyone who is building an infrastructure-heavy clean energy company and might need to think about where the DOE is looking from ensuring we have enough equipment and enough material to meet the needs of some of the key technologies that the DOE is leaning in on.
I am very glad to give that plug. I can't wait to listen to that now.
Awesome. Well, Arvin, I'm so grateful for you for joining us and taking time out of your busy day to share more about what you're building, and really looking forward to watching the journey ahead for you.
Awesome. Thanks, Cody. Thanks, everybody, for listening.
Inevitable is an MCJ podcast. At MCJ, we back founders driving the transition of energy and industry and solving the inevitable impacts of climate change. If you'd like to learn more about MCJ, visit us at mcj.vc and subscribe to our weekly newsletter at newsletter.mcj.vc. Thanks, and see you next episode.